There are two ways to create objects in C++. One, the stack, and two, the heap or the free store. We've been discussing pointers and kind of practicing and using pointers in projects so far. And we looked at pointers and pointees, how to set up a pointer, how to dereference a pointer, when you should pass by value and passing by reference using both pointers and references or aliases. But one of the more powerful things you can do with pointers is create and access objects on the heap or the free store in C++. So let's look at that, and we'll quickly discuss the difference between the stack and the heap. Let's look at creating simple data types on the stack. And the stack is pretty much what we've been doing up until now. We've been creating variables on the stack, and let's say I'm going to store the value 10, and I'll make a variable a. This declares a. Its data type is an integer, it's on the stack, and it now holds the value 10 via the assignment operator. Alright, I'll make a variable b, and I'll hold the value 20, and c, and we'll hold the value 30, and d, and we'll hold the value 40, respectively. Okay? So I have these variables, and when I do, I create them one by one. So I'm going to come over here to kind of simulate that. A, and then b, and c, and d. Alright? And each of these in the memory registry would be assigned basically a hexadecimal memory address. Remember, integer is a 2-byte value, and each byte is composed of 8 bits. But to access them, then we need that address. Well, on the stack, let's say that I were going to perform an operation like this. If I were going to, let's say that I want to take the value that's in D and I want to store it inside of A. Okay, if I were going to do that. To access the values in these variables on the stack, it's not the most efficient way to do it. Because if my pointer were here, and now all of a sudden I need to go fetch the value of A, all of these values have to be moved up the stack. Sort of like, you ever go to one of those buffets and they have a stack of dishes that pop up on a spring? Well, you could think of the stack sort of like that, and all the objects or variables sitting on it have to kind of be moved around back and forth in order for the computer or the CPU to access different objects stored in different locations on memory. So it's not the most efficient way of doing things. Now, that's not a big deal with the 2-byte structure, but imagine you had your own class that you wrote that was hundreds of bytes or thousands of bytes, which is typical in larger applications today, or games or multimedia projects and things. Okay, so although that is it's a simple way to create things, it's not necessarily the most efficient way to create things, and that's the stack. Now let's look at creating simple data types on the heap. Now the heap is totally different. Okay, we'll come down here, and if I were going to create something on the heap, everything on the heap has to be accessed indirectly or via indirection. In other words, via a pointer. So I need to make a pointer to the right data type before I can build my object on the heap or the free store. In other words, I couldn't make a pointer to a double if I were going to store an integer. 8 bytes and 2 bytes are not the same. Or I couldn't make a pointer to a character, 1 byte and 2 bytes. And I wouldn't want to make a pointer to a string, or I can't even spell that. Type and talk at the same time, but you get the idea. So the data type needs to match, all right, or coincide with what we're going to point to. So I'll make a pointer to an integer, okay, and I'm going to call this PA. And then this is going to point to an object that I'll build or I'll create on the heap or the free store. And so I'm going to use the keyword new, and I'm going to call the constructor for an integer. All right, so all of your simple data types have constructors, just like classes of objects that you write. So I'm simply calling the constructor for an integer. And I'll do the same thing, all right? I'll do int, and we'll call this PB, or a pointer to... Now this is not the same as... Don't get confused with the previous example, or 2 examples ago. We were creating pointers, and we were creating integers on the stack, and then assigning pointers to the address of those integers. But this is not the same thing. Here, this pointer points to an integer that's actually on the heap or the free store. All right, it's not being reassigned to point to something else. But I'm simply calling the constructor and building that object. All right, same thing. So I'd make a pointer, PC, call the constructor, make another pointer, PD, use the new keyword, and call the constructor. So just an example of simple data types. And if I did that, all right, by building new integers here, what happens is, let's say that I make A here, okay? And let's say that I make a few other variables, and B is here, and C is here, and let's say that D is here, okay? This represents the heap or the free store. And everything on the heap or the free store, unlike the stack, is accessed via a pointer. Well, a pointer is less than a byte. And again, it might not be a big deal with a small data type like an integer, but imagine you have large objects, hundreds or thousands of bytes big. Accessing those objects via a pointer and just moving the pointers around instead of having to move the whole object around offers a tremendous advantage. The analogy we could draw is, imagine you have two identical rooms, and let's say that they're furnished identically. There's 20 computers, it's a classroom, there's 20 computers and there's 10 tables and a teacher's desk in each room. Well, that's kind of like what your memory registry is. It's composed of billions of bytes having 8 bits each, and so you could think of it as identical rooms. Well, what's easier? To take all the objects in one room, all the data, and physically move it to another location, another room? Or let's say that you're in room 147 and someone else is in room 148. What if you just swap the signs? Given the choice, what's easier? Moving out all the furniture from room 147 into room 148 and moving all the furniture in 148 to room 147, that would take a long time. It would achieve the same result, but if they're furnished identically, if there's no difference between the rooms, then all you really have to do is change the sign on the door. So the 147 sign is replaced with 148, and the 148 sign is replaced with 147. Just trying to build an analogy, but maybe that will give you an idea about the heap or the free store. That's a lot more efficient, it's a lot quicker, it's a lot easier, it's a lot less demanding on system resources, uses less memory than trying to move things around on the stack. And so now when I need to get at any of those values, now that will fundamentally change how I access it. If I were going to display the value of A, sorry, I gotta clear my throat there, but if I were going to display the value of A, then I would simply call up A, right? That's on the stack. But since I've built PA, it's an integer on the heap or the free store. It's a pointer, right? So and then I have to dereference it, so PA, and right now it's null. We haven't given it a value yet, we've just created it. But that would show you how to display it, okay? So displaying an object on the stack, I have to dereference to display an object in the heap, because everything on the heap is accessed via pointers. We're not moving objects around, we're just moving pointers to the objects. Objects, stay put, stay where they are, unlike the stack. Alright, so let's assign some values to our objects on the heap or the free store, and then we'll compile it and we'll run it just to kind of show the difference there. So again, think about it. Think about the basic rules of a pointer. Since we've already gone through 2 videos dealing with pointers, if I'm going to assign a value to an object a pointer points to, can I assign it directly? In other words, can I do this and store, let's say I want to store the value 100 in PA. Is that allowed? PA being a pointer. Right, we can't do that. No, we can't assign a value or store a value in a pointer. We have to dereference the pointer to get the variable that it points to. And then at that memory address or location, we can then store a value, 2-byte value 100. Okay, so using the same principle, then we want to do the same thing for the other 3. So again, if we're going to assign a value, 200, all right, let's dereference PC, give it a value 300. And let's dereference PD and YPD, no, but PD. Alright, so if we do that, now we have values. Alright, so let's build it. I'm not going to do much at this point other than just show us the value of A and PA. But alright, so our syntax is good, and let's run it. Alright, so we're dereferencing PA. Now, A is on the stack, PA is on the heap or the free store. So what about the other 3 values there, the remaining values? Again, if we're going to display this, I'll just copy and paste this to the clipboard here. Alright, and we'll modify it to taste accordingly. Okay. And there you go, 4100, 2200, 3300, 4400. Let's look at building programmer-defined class objects on the heap. Okay, so that illustrates the use of a simple data type in both creating something on the stack and the heap or the free store. Now what if it's a class that we read ourselves? In other words, a user-defined or programmer-defined data type. In this case, let's build a cat. Alright, we'll build a cat class. And we'll call it kitty. How about that? Alright. We'll make a simple constructor and a simple destructor. Just let us know we're building the kitty. Just let us know we're destroying the kitty. Oh, how awful. It sounds so horrible. Not really destroying the kitty. It's just virtual, of course, but hey. Alright, and let's make these public. Not pubic. Oops. My bad. Public. And, alright, let's see. Let's see. What are we going to do in our kitty? Give our kitty some methods. So a member method and kitty's meow. Meow. So let's make our kitty meow. Alright, kitty meowing. And let's add a couple of variables, some data members in here. So we'll add kitty name and kitty age. How about that? So those will be our private data members, and let's just write a couple of accessors to get at it in our public area. So for the set kitty name, and we'll need to accept an argument in the form of a string. Let's call it x. Kitty name. Alright, and let's do a get. And it needs to return the matching data type. Get kitty name. Doesn't need to take any arguments or parameters, just a keyword return. And the private data that we need to access. Return kitty name. Okay. And let's again code a set and a get for kitty age. And let's see. And we need to take the right kind of argument, so it's an integer. And alright, kitty age equals x. And for our return, or for our get, we need to return the right data type, which is an integer. Kitty age. Don't need to take any arguments though. And just need to return kitty age. Alright, so we have a basic kitty now. And there is our kitty class. And here I'll wrap some comment tags around it so it looks, try to make it easier to follow here. Alright, so there's our basic kitty object. Programmer defined or user defined kitty. Let's make sure that our kitty is good. Might have messed up on our kitty. Let's see, kitty age undeclared. Oh, yeah, a typo there. Why didn't you guys tell me? Oh, wait, that's right. You couldn't. And then let's see, what are we doing? Oop, left out my parentheses there too. Boy, all kinds of mistakes here. Alrighty then. Alright, so there's our kitty. Alright, so there's our basic kitty. Now, this is an example. I'm going to push all this down here. And we'll just wrap it in some comment tags to kind of get it out of the way for now. Who knows, maybe we'll make use of that later. Alright, so how would I build a kitty on the stack? You know, given this example, how do we build the integers on the stack? Right, that's just a plain Jane normal way of, alright, so kitty and Felix and kitty Garfield. Okay. And kitty, who's another famous cat? Heathcliff. Alright, so there's 3 famous kitties. Now these are on the stack. Oop, can't even spell stack right. Can't type and talk at the same time. Okay, so if I build my kitties on the stack, that'll call the constructor. And then how do I access a function or a data member? Right, the dot operator. Okay, so in other words, it would be the instance name, right? Not the class name, that's just a blueprint. But the instance name, Felix, dot, let's say I want to make him meow. Okay, I want to make him meow. Now Felix is going to meow. Let's say that we want Garfield to meow. Alright, and then Garfield will meow. Let's say that we want to set the name on Heathcliff. Okay, and then we'll say Heathcliff dot set kitty name and pass in a string variable Heathcliff. Alright, let's say we want to get his name and get kitty name, and let me just pass that into cout. We'll just do a little concatenation there. The current kitty name equals. Now we'll do Heathcliff. Alright, so the only point I'm trying to illustrate is, okay, we built all these on the stack. Notice that all of them are accessed via the dot operator in C++. And that works just like Java. Sans the new. In Java, you'd use the keyword new to build a class of object, but even in spite of that, you'd still use the dot operator. Well, in C++, you only use the dot operator when you build a class of object on the stack, like so. Okay? So let's build that and check our syntax, and let's run that. It doesn't do much, but it'll illustrate a point. Calling 3 kitty constructors for Felix and Garfield and Heathcliff. Kitty meowing, and which one was that? I can't even remember. Okay, Felix is meowing, Garfield's meowing, Garfield meow. Current kitty name is Heathcliff because I set the kitty name. Okay, so that'll illustrate the point there. Now let's build some kitties. We'll build some new kitties. In this case, we're going to build them on the heap. All right. So if I come down, let me just bring this code down here and we'll comment it out. Alright, that was the stack, or that example was the stack. Now this is the heap or the free store. Doesn't really matter, same thing, but some people call it by different terms. Potatoes, potatoes, tomatoes, tomatoes. Alright, so if I want to build a kitty on the heap or the free store, it's always got to be with a pointer, right? So I start out with a pointer to the right data type. I can't have a pointer to a dog. Boy, that'd be a Frankenstein accident. I can't have a pointer to an integer. It's got to be a pointer to a kitty. So a pointer to a kitty, a user-defined class or data type. Here's our blueprint for a kitty up here. There's our class. Alright, so a pointer to a kitty, and what if we just call it pFelix? We could call it Felix too, but if I decide to uncomment this code, then I'd have a problem. I don't want the pointer to have the exact same name as the actual kitty on the stack. So it's common. A lot of programmers put a little lowercase p in front of things. People that like Hungarian notation and so forth, whatever. You can come up with your own system, but I'm just going to prefix it with a p. Okay? So there's my pointer to get at the kitty that I'm going to build on the heap or the free store. It's not an actual kitty, but it's a pointer to a kitty object to get at it once we build it on the heap or the free store. So now I'm going to use the keyword new, just like I would in Java. I'm going to build a kitty. I need to call the kitty constructor when I do that. Okay, so using that example, how would I then build Garfield, the next kitty? Exactly. A pointer to a kitty object. We can call it anything we want, banana, but tradition says we will typically prefix it with a little lowercase p. Alright, so there's Garfield. And use the keyword new and call the kitty constructor again. Alright, and how would I build Heathcliff? Exactly. You got it. He thinks you got it. Alright, so Heathcliff, there's my pointer, and let's call the keyword new. And again, my kitty constructor, my syntax is okay. I spell everything there. If not, we'll find out when I compile it. All right, so now that's one thing that changes. Notice the difference. Here's how we built it on the stack. Here's how we built the kitties on the heap or the free store. That's one thing that changes. Another thing that changes is how you access a member method or accessor method or a data member from the class itself. Instead of using the dot operator like you would in Java, even when you do use the keyword new, when you use the keyword new in a pointer to build something on the heap or the free store in C++, you use the arrow. It's just a dash and like the greater than symbol. So in other words, if I'm going to access the same functions here, if Felix is going to meow or pfelix, then I would use the pointer name and the arrow, all right, from pfelix, and then I call meow. And if Garfield's going to meow, it'd be Garfield and the arrow, and then he's going to meow, okay? And if Heathcliff is going to do his thing, what do we do? Set kitty name. Excuse me, that was P Heathcliff. All right, so and set kitty name, and wait, I'm avoiding F today for some psychotic reason. Okay, my own little neurosis there. All right, set kitty name, P Heathcliff. All right, looks good. And then let's fetch or get the kitty name. All right, so again, we'll simply say okay, and let's call P Heathcliff. And again, instead of the dot operator, it would be the arrow because this object is on the heap. And we'll call get kitty name to return a string. All right, and let's see if I made any. All right, so again, just kind of look at the code, the differences between the heap and the stack, but let's build this project, check our syntax, and run it. I'll run it. You can see that it does the exact same thing. There's really no difference, okay? But behavior-wise, efficiency-wise, there's a profound difference. These objects are accessed more efficiently. They're on the heap or the free store, but they must always be accessed via a pointer, okay? And likewise, these objects on the stack are accessed less efficiently. Dot operator, arrow, passing objects created on the heap to functions by reference. The other thing that will change is when you have a function that accepts arguments. If you have an object built on the heap, think about it. pfelix, pgarfield, pheathcliff, they're already pointers. They're not actual objects on the stack. So if I were passing these to a function that accepted arguments via a pointer, then I wouldn't have to use the ampersand or the address of operator. They're already a pointer. They're on the heap. So I would just pass them in as pointers, and they would go in as pointers. If that seems convoluted or confusing, perhaps I need to explain it a little bit better with an example. So we'll code a quick function that accepts two kitty objects via pointer, so therefore by reference. And let's see, we'll define it, so we don't have to prototype it. This time we're going to define it before main, okay? And it'll have no return type, it'll be void. And let's see, what are we going to do here? We'll call it kitty fight. All right, so we'll have a kitty fight, and we'll take two objects. All right, so in our kitty fight, we'll take kitty opponent 1, feline combat, and kitty opponent 2. All right, so 2 pointers to kitty objects, one called opponent 1, one called opponent 2. Now, what on earth are we going to do with our kitties? We'll have to think of something to do with our kitty that's not too brutal or unacceptable. Terrible. All right. So let's see, opponent 1 and opponent 2. What can we do with our kitties? First off the bat, opponent 1, let's see. Let's get the kitty name. Opponent 1, get kitty name. We'll just say this, I'll tell you what. Just to illustrate the point here and make it short or keep it brief. We'll just have a simple output statement. And let's throw the. I'm going to throw this on a second line here in my concatenation. So that. All right. Boy, I cannot type today. Alright, scratch, there we go. Alright, so that'll just be for the purpose of illustrating when we pass these objects in here. And let's see, let's check our syntax real quick. Okay, so we have a function now that takes arguments by reference utilizing pointers. Right, therefore we have to use the arrow. That's how we're accessing the object in the function. Now let's look at passing different kinds of kitties back and forth. Okay, and so to illustrate the point, I'm going to move this over here. Alright, put that in our, let me put that in our commented out code. And let's see, I left all that in there from the stack. I don't know why I'm keeping all this. Maybe I'll use, who knows. I'm always afraid to delete something because you never know, you want to reuse your code, but I'm just a pack rat. We don't need that. Anyway, so we have these objects on the heap, and let's build some objects on the stack as well. We'll come over here and we'll need to, let's, even though they are different names, it does have a P in front of it, we'll give them different names here. Fluffy, Daisy, and Rufus. Alright, so you have Fluffy, Daisy, Rufus, Felix, Garfield, and Heathcliff. They're all different there. Alright, so how does this fundamentally change if I'm going to call this function here that accepts kitty objects via pointer? Right, or in other words, passing by reference and not by value. So let's say we actually want to use our function. I'm just going to rename it to kitty combat instead of kitty fight because it's cuter. What can be cuter than two kittens playing together, wreaking havoc on your furniture? Anyway, so we're going to call it kitty combat, and it expects as its set of parameters or arguments two pointers to kitty objects, not two actual kitty objects, but two pointers to kitty objects because we're passing by reference. So let's say I were to pass in Fluffy and Rufus here. They're built on the stack. Alright, that would be a syntax error if I compiled that because these are actual kitty objects on the stack. They're not pointers. I'd have to use the ampersand or the address of operator. But to illustrate the point, I'll compile it and we'll look at the error message generated. Alright, so pointer to kitty and kitty, we can't convert there. Now on the other hand, if I use the ampersand, we'll use the ampersand here and rebuild the project. And lo and behold, it runs. Alright. And so let's run it. These are our two kitties on the stack. Let's run it and see what happens. Building a kitty and 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 a kitty. And then attacks. Oops, you know what? I guess we should set a name here. Why don't we set names on Fluffy and Rufus? Might be good, eh? So Fluffy and let's excuse me, set kitty name, wasn't it? Alright, let's set the name attribute Fluffy and Rufus. Set kitty name was Rufus. Alright, there we go. So we have kitty name set now. Let's rebuild that and let's run that. Alright, so now Fluffy attacks Rufus and let's just add a little escape sequence here. We'll just concatenate, drop down 2 lines and maybe tab over there. Just kind of separate that from so you can see the constructor calls. Alright, so here's the constructor calls. And notice that, in this case, even though we're passing by reference, look what's happening. We're building a kitty, 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 calling the constructor 6 times. The first 3 were on the heap, the last 2 were on the stack. We pass in Fluffy and Rufus. and everything works. But not necessarily the most efficient way, but it works. That's because we used the ampersand and we passed in the address of Fluffy and Rufus and not the actual Fluffy and Rufus. Now on the other hand, what if we were going to pass in Felix and Heathcliff? In which case, if we did that, let's also set their names. Got to use the arrow this time, right? And what was it, capital N? Who would win, Felix or Garfield? I don't know. Well, this time we'll pass in Garfield and Felix. Yeah. All right, so second name Garfield. Let's see, second name. Why do I keep doing that? Felix. Anyway, Feliz, happy. I must be happy. Anyway, if I did that and I passed these objects in, now it's tempting to think, well, you're used to using pointers. I'm going to use the ampersand. I'm going to, I'm passing by reference. But here's the thing: P Felix and P Garfield, they're already pointers to objects on the heap of the free store. So I don't need the ampersand. I don't have to use the address of operator. I can just say P Felix and P Garfield. Alright? P Felix and P Garfield. If I tried to use the ampersand, that would actually be an error. And I'll illustrate the point. Let me compile this. See, no syntax errors. Now what if I tried to do this and this, like I did with the objects on the stack? Cannot convert, and see here it's like a double dereferencing almost. But this is a situation, since they're on the heap or the free store, everything on the heap or the free store is accessed via a pointer. So when you pass objects in, to a function that accepts something by reference using pointers, you don't need to use the ampersand or the address of operator. If it's on the heap, it already has a pointer that points to the object on the heap. Finally, remember to delete pointers to objects on the heap that you are not using any longer. Last, when we construct an object on the heap or the free store using a pointer, and we're done with it, we need to call delete on that object, and then that'll free up that memory if it's needed. Now the object will persist in some compilers in memory until that space is needed, and then it can be written over. It won't necessarily erase the object that's there, but that will simply deallocate the space and free it up if it's needed. And programs that forget to do this waste memory, and they generate memory leaks. Maybe you've encountered applications in the past where you'd run them, and after a while you notice you get less and less memory, and you have to either end the program or even reboot your operating system to gain some of the memory back. So we want to clean up after ourselves, so to speak, when we build objects on the heap or the free store, when we're done with them. So as long as they need to persist in memory, that's fine. But let's say that we're done with our kitties here at the end of our program. So that would be after kitty combat. So we have 3 kitty objects on the heap: P Felix, P Garfield, and P Heathcliff. And what I would do is I'd simply say delete P Felix, delete P Garfield, and delete P Heathcliff. Alright? And that would have the effect of cleaning up those objects. And you can see here, the destructor is being called destroying a kitty, destroying a kitty, destroying a kitty. So that wipes those objects, or deallocates the space that's allocated for those objects on the heap or the free store.